Hello everyone. Quick thought to start. Why does a pulley make lifting a bucket feel easy, yet your arms still get tired? Today we'll uncover the principle of a machine, the idea that a machine doesn't create energy, it only transforms or transmits it. In an ideal world with no friction, the work input equals work output. I'll say that aloud as an equation, W in equals W out. In real life, some of the input becomes heat, sound, or deformation, so W out is less than W in. As you can see in the diagram, imagine energy flowing into the machine as input work and splitting into two parts, useful output work and losses. So when a pulley makes the force smaller, it quietly demands you to pull a longer distance or for more time, keeping the energy balance honest. That's the heart of every machine you use, from scissors and screw jacks to bicycles and cranes. Work input is the total work done by the effort on the machine. It is calculated as the effort multiplied by the distance moved by the point of effort. Work output is the useful work delivered to the load, found by multiplying the load by the distance the load moves. In an ideal machine, the work input equals the work output, meaning the effort multiplied by its distance is exactly equal to the load multiplied by its distance. In a real machine, some of the input energy is lost as friction, deformation, or other inefficiencies. So the work input equals the work output plus these losses. Work is measured in joules, where 1 joule is defined as 1 newton of force acting, through a displacement of 1 meter in the direction of the force. Mechanical advantage is the factor by which a machine multiplies the applied force. It is calculated as the load divided by the effort. This ratio has no units and can be greater than 1, equal to 1, or less than 1, depending on the purpose of the machine. When the mechanical advantage is greater than 1, it means a smaller effort can lift a larger load. When it is less than 1, the machine is sacrificing force in order to gain speed or increase the distance of movement. Mechanical advantage depends on both the geometry of the machine and the effects of friction. Even for the same machine, the mechanical advantage can vary under different loads because frictional forces can change. For example, in a crowbar, which is a type of lever, increasing the length of the effort arm increases the mechanical advantage, allowing the same load to be lifted with less applied effort. Velocity ratio is the comparison of movement distances or speeds in a machine. It is calculated as the distance moved by the effort divided by the distance moved by the load. A key property of velocity ratio in an ideal machine is that it depends only on the geometry of the machine, not on friction. This could be determined by factors such as the number of supporting pulley segments or the lengths of the arms in a lever. When the velocity ratio is greater than 1, it means the effort point moves farther than the load. This arrangement trades distance or time for a gain in force. For example, in a 2-to-1 pulley system, the load rises only half the distance that the effort is pulled, giving a velocity ratio of about 2. The efficiency of a machine measures how effectively the input work is converted into useful output work. It is calculated as the work output divided by the work input, multiplied by 100%. Since the work input is the effort multiplied by the effort distance, and the work output is the load multiplied by the load distance, efficiency can also be written as load times load distance divided by effort times effort distance multiplied by 100%. This simplifies to mechanical advantage divided by velocity ratio multiplied by 100%. In an ideal machine, efficiency is 100%, and the mechanical advantage equals the velocity ratio. In a real machine, efficiency is always less than 100% because of losses caused by friction, deformation, or slippage. Efficiency can be improved by reducing these losses. For example, through lubrication, the use of ball bearings, smooth surface finishes, and rigid components that minimize unwanted flexing. In an ideal machine, the principle of the machine states that the work input equals the work output. This means the effort multiplied by the effort distance is equal to the load multiplied by the load distance. By rearranging this relationship, the load divided by the effort equals the effort distance divided by the load distance. In other words, the mechanical advantage equals the velocity ratio when there are no losses. If the mechanical advantage is less than the velocity ratio, it indicates that the efficiency is below 100%, with the exact value given by efficiency equals mechanical advantage divided by velocity ratio multiplied by 100%. This relation is a quick and useful check when solving numerical problems, because if you know any two of the three quantities, mechanical advantage, velocity ratio, or efficiency, you can immediately calculate the third. Let's work through an example. A machine lifts a load of 300 newtons through a vertical distance of 0.25 meters. The effort moves 1.50 meters, and the applied effort is 80 newtons. We need to find the mechanical advantage and the velocity ratio, then calculate the efficiency, and finally determine the effort that would be required if the machine were ideal. First, the velocity ratio is the effort distance divided by the load distance. That is 1.50 divided by 0.25, which equals 6. Next, the mechanical advantage is the load divided by the effort. This is 300 divided by 80, giving 3.75. For the efficiency, we divide the mechanical advantage by the velocity ratio and multiply by 100%. That's 3.75 divided by 6 multiplied by 100, giving 62.5%. Finally, in an ideal machine, the mechanical advantage equals the velocity ratio, which is 6 in this case. The ideal effort would then be the load divided by the mechanical advantage, or 300 divided by 6, which equals 50 newtons. Let's wrap up. A machine can't create energy, it only channels it. In symbols we kept repeating W in equals E times D sub E, W out equals L times D sub L, and ideally W in equals W out. That leads to M A equals L over E. We are equals D sub E over D sub L, and the efficiency relation eta equals open bracket MA divided by we are close bracket times 100%, with MA equals we are only in the frictionless ideal. From levers and pulley blocks to gears and jacks, engineers tune geometry to get the force distance trade-off they need, then fight losses with good materials, lubrication, and design. I hope the energy picture behind machines now feels intuitive. When force goes up, distance usually pays the price. See you in the next session, where we'll apply these ideas to specific machine types and sharpen your problem solving even more.